Welcome back to the Geometry International Honors Summer Assignment Help video series. In this video, we are going to work on Part D and look at some examples of solving systems of equations. The directions on the summer assignment will ask you to solve a system of equations using either substitution or elimination, and then you're asked to write your write your solution as an ordered pair. Remember, the solution to a system of linear equations would be the coordinates of the point where the two lines intersect, if they do intersect. So this first example, it looks to me like this would be a good example of a problem where we want to solve using elimination. And the whole point of elimination is to eliminate either the x or the y. And you can do that by either adding the two equations or subtracting the two equations. Now, as you look at these x's and look at these y's, neither adding nor subtracting will get rid of either an x or a y term. Remember, that's why it's called elimination, is because we want to eliminate either an x term or a y term. So what we're going to have to do is make a choice. I think I'm going to choose to add the two equations. And if I were to add the two equations and I'm looking at the y terms, that top equation has a coefficient of 2 on the y term. If this coefficient were also 2, then when I go to add the two equations, the y terms would eliminate or drop out. So to do that, I can look at the second equation, and what I'm going to do is I'm going to multiply both sides of that second equation by 2. Remember, you can do anything you want to an equation as long as you do the same thing to both sides. So what we'll do now is rewrite the first equation, the top equation. 3x plus 2y equals 4. That equation remains unchanged. And then the bottom equation, we're multiplying every term by 4. Every term by 2. So the bottom equation will be 4x minus 2y equals negative 9 times 2 is negative 18. So now when I add the two equations together, 3x and 4x gives us 7x. The y terms are eliminated or cancel out, and then our constant term would be 4 plus negative 18, which is negative 14. Dividing both sides by 2, I get that x is equal to negative 2. So at this point, we're halfway done with our problem. We have found the x value of the point where the graphs of these two lines intersect. So now what we need to do is, now that we have the solution for x, I can go back to either equation, and it doesn't matter which one I choose. I'm going to use that second original equation before I multiplied both sides by 2, the 2x minus y equals negative 9. And where I see this x, I'm going to replace it with a negative 2, and then I can solve for y. So rewriting that equation, that second equation. So rewriting the second equation, it would be, let's see, 2x minus y equals negative 9. And where I see this x, I'm going to replace it with the negative 2. So we would have 2 times negative 2 minus y equals negative 9. Or negative 4 minus y equals negative 9. I'm going to add 4 to both sides and get that the opposite of y is equal to negative 5. Be careful and don't lose this negative sign in front of the y. And if the opposite of y is negative 5, well then y must be positive 5. Okay, so the directions ask you to write your answer as an ordered pair. So an ordered pair is called an ordered pair because the order is important. The first value would be your x value, and the second value would be your y value. So we'll write our final answer as negative 2, positive 5. Here is another example where we can use elimination to solve this system of linear equations. And so looking at the coefficients of x and coefficient of y, right now if I were to add or to subtract the two equations, neither the x terms nor the y terms would be eliminated. So what we need to do is look at those coefficients and make a choice. This time I'm going to choose to subtract the two equations, and I'm going to focus on the x terms. And looking at their coefficients, I have a coefficient of 3 and a coefficient of 5. The least common multiple of 3 and 5 is 15. And if both of these terms had a coefficient of 15, well then when I subtracted the two equations, the x's would drop out. So what I'm going to do is rewrite both equations. The first equation, I want the x term to have a coefficient of 15, so I'm going to multiply by 5. Now if I multiply the left side of the equation, make sure we also multiply the right side of the equation by 5. And then looking at the second equation, this x, I want this coefficient to also be 15, and I can accomplish that if I were to multiply both sides by positive 3. And again, make sure you multiply both sides of the equation. That's a common mistake that students make, is they only multiply one side of the equation by constant. So make sure you multiply both sides. So now we're going to rewrite both equations. The new top equation will be 15x minus 10y equals 10. I multiplied every term on both sides by 5. And then the second equation will be 15x plus 9y equals negative 9. And again, I multiplied every term on both sides by 3. So now notice that if I were to subtract the two equations, these x terms are going to drop out. So let's do that. 15x minus 15x, those cancel. Now be careful with your signs here where I have a negative 10y, and I'm going to subtract 9 from that. Negative 10 minus 9 more will give me negative 19y. Oops, that's not right. Hold on, let me fix that real quick. Sorry about that. That should be negative 19y. And then on the right side, 10 minus, we're going to take positive 10, and I'm going to subtract a negative 9. Remember, subtracting a negative 9 is the same as adding a positive 9, so I'd end up with positive 19. All right, then we'll divide both sides by negative 19, and I have my y value. Oops, sorry. There we go, negative 19. I have my y value. Positive 19 divided by negative 19 gives me negative 1. So there's half of my solution. To find the x value now, I'm going to go back to either equation. It doesn't matter which one I choose. I think I'll just choose this bottom one. And where I see a y, I'm going to replace it with negative 1. So let's do that. So the original bottom equation was 5x plus, instead of 3 times y, I'm going to write 3 times negative 1, and that's equal to negative 3. So we'd have 5x minus 3 equals negative 3. And then adding 3 to both sides, we get 5x is equal to 0. And then when I divide both sides by 5, we get x is equal to 0. So the point where the graphs of these two lines intersect then would be at the point 0, negative 1. Taking a look at this next example, we can see that this might be a really good time to use the substitution method because the second equation is solved for x. So what we can do, since the second equation is solved for x, is I can take the top equation, and where I see this x, I'm going to replace it with what x is equal to. I'm going to replace x with negative 5y minus 2. So what we're going to do is rewrite the top equation, and we'll have 4 times. Now I'm going to start some parentheses because now instead of writing an x right here, I'm going to replace that x with what it's equal to, negative 5y minus 2. So we have 4 times parentheses, negative 5y minus 2, close those parentheses. Now keep going. I've just rewritten the x. Now write the rest of the equation. So I need to write minus 2y equals 14. So I'll do that. Minus 2y equals 14. Now when you take a look at this equation, do you see that there's only one type of variable? There's only a y. So that means that this equation can be solved for y. So let's do that. We're going to start by simplifying and getting rid of these parentheses. So I'd have negative 20y, and then minus 8 minus 2y equals 14. Let's go ahead and let's combine these like terms. So we'd have, let's see, negative 20 minus 2 more would be negative 22y minus 8 equals 14. Then we'll add 8 to both sides, and we'll have negative 22y equals 22, and then to solve for y, we'll divide both sides by negative 22, and we have our y value is equal to negative 1. So now, again, we're halfway done with our solution. We have the y value of the point where the graphs of the two lines intersect. So now to find the x value, that's going to be very simple. Notice the second equation is already solved for x. So if I take this negative 1 and plug it in for y, then all I have to do is a little bit of arithmetic, and we have our y value. So we have x equals negative 5 times, let's replace that y with negative 1, minus 2 more. So x is equal to 5 minus 2, x is equal to 3. So the coordinates of the point where the graphs of these two lines intersect will be at the point 3, negative 1. Make sure you write your answer as an ordered pair. This next example looks like a good time to use substitution again, because notice the first equation is solved for y. So what we can do is go to the second equation, and where I see this y, I'm going to replace y with what it's equal to. So I'm going to rewrite the second equation and write it as negative 2x plus, now instead of writing y, I'm going to write the expression that y is equal to. Y is equal to 2x minus 1. So we'll replace that y with 2x minus 1, and then that's going to be equal to negative 3. When I simplify, I have, let's see, oh, look what's going to happen here. Negative 2x plus 2x cancel, so the variable drops out, and we get this expression, negative 1 equals negative 3. Well, of course, negative 1 is not equal to negative 3. So let's talk about what that means. If you're solving algebraically and at some point the variables drop out and you end up with a statement like this that is not true, what that means is that there is no solution. What does no solution mean? Remember, we're trying to find the point where the graphs of these two lines intersect. So if there's no solution, if there's no point of intersection, what does that mean? Well, what that means is that these two equations are actually the equations of parallel lines. Let me just draw a pair of parallel lines, and you'll notice that parallel lines never touch each other, and they never have a point of intersection. So if you have a problem like this, where again the variable drops out at some point when you're doing the algebra and you end up with a non-true statement, you can stop right there and say, well, there's no solution. In other words, the graphs of these two lines are parallel and they'll never intersect. And let's try one last example. I think this time elimination might be the way to go. And how about, let's just get the matching coefficients on the x terms, and then we'll subtract the two equations, and when we subtract the two equations, the x's will drop out or be eliminated. So to make that happen, let's go ahead and multiply. We'll multiply that top equation by positive 3. Make sure you multiply both sides by 3. So the new top equation is going to be negative 9x plus 3y equals 3. I multiplied every term on both sides by 3. And the second equation was negative 9x plus 3y equals 3. So notice we have two equations that are exactly alike. If I try to continue at this point and try to subtract the two equations, well, I'm going to get 0 equals 0. Now, of course, that's a true statement. So unlike the last example where the variables dropped out and we had a false statement, this time the variables dropped out and we have a true statement. So what that means, you can see right here algebraically, we're looking at the equation of the same line, okay? So if the variables drop out and you end up with a true statement, you actually have what we call, I'm going to write it down for you, the fancy math word is coinciding lines. Yeah, I spelled that right, coinciding lines. So coinciding lines just mean you have one line that lies right on top of another line. Okay, so what that means is every point, the coordinates of any point of one line will satisfy the equation of will satisfy the either equation or both equations. So in other words, we have an infinite number of solutions. So at this point, if your variables drop out and you end up with a true statement, you can stop right there and say there are, and I want you to write it like this, an infinite number of solutions. Infinite number of solutions. In other words, there's an infinite number of ordered pairs whose coordinates would satisfy both equations at the same time. I hope these examples will help you be successful on Part D of your summer assignment. Of course, if you have more questions on the summer assignment, be sure and ask me at school.